We are in section 10.2, regression. This section introduces a method used for finding the equation of the straight line that best fits the points in a scatter plot of paired sample data. The best fitting straight line is called a regression line, and its equation is called the regression equation. We can use the regression equation to make predictions for the value of one variable given some specific value of the other variable. The regression line, or the line of best fit, or the least squares line, and there's so many different names for this line, just to be aware of that, is a straight line that best fits the scatter plot of the data. The regression equation is given as y hat equals b naught plus b1 times x. I want you guys to realize that this is also going to be written a little bit different from the calculator, and then also from what we learned in algebra. So just to be aware, b naught and b1 are just variables. Algebraically describes the regression line. The regression equation represents a relationship between x, which is called your explanatory variable, so that's our x, and or predictor variable or independent variable, and y hat, which is called our response variable or our dependent variable. And then there's a little note here. The explanatory variable is used to predict the response variable. And right below that is a box that we need to give a star to. And that says, find the equation of the regression line with a TI-8384 calculator. Requirements are that we have to have a simple random sample of quantitative data. Our scatter plot has to show that it's approximately linear. We discussed that in the last section. Data contains no outliers. If there are any, you need to remove them. And we're going to input our data into L1 and L2, and then we're going to go to stat test F, which is linreg t-test. So referring back to page 1 of our notes, remember that this is F linreg t-test. We had an input that we put in. In our linreg t-test, we're going to have an equation. So this time we're looking at our equation, and the way that the calculator writes it is y equals a plus bx. Now again, be aware that a and b are just variables. They can be called m and b like they are in algebra, b naught, b1 like they are in the notes. There's a lot of different ways to write this. And I want you guys to realize though that a and b are given to you. So we have a and b down here. And so these two values that we have, you need to substitute into your equation up here. And those values, again, determining those values is going to depend on the data, and they will be different than what is typed here. And so you need to round it appropriately, and it's different for every single problem, and substitute those values in for A and B. So the next example says, using the bill tip data, find the best predicted tip amount for a dinner bill of $100. What tipping rule does the regression equation suggest? And from this, we need to go to linreg t-test on our calculator. We did that in the last section. From our output earlier, we get an equation for our regression line, which is y equals a plus bx. And then we also have our values for a and b that are given to us. We need to take those values, round them correctly, and then substitute them in to our regression equation up above. Y hat is equal to, and we're going to go ahead and round 3 decimal places here, and our a value is negative 0.347 plus our b value is 0.149x. And I want you guys to realize that in algebra, we usually didn't write it this way. We usually wrote that x value first. That was our slope, and we'll get into that later. But you can also write this and switch around those variables. But I want you guys to realize that that 0.149 always stays with the x. That is the slope. And again, we'll get into that later on. And so either one of these is going to be okay to use. There's another question on here that says, what tipping rule does the regression equation suggest? And so that rate that we have would be your slope. and your slope here, either looking at the first equation or the second equation, is going to be, and rewriting this as a percent would be 14.9%, and that would be your tipping rate. So almost 15% would be our tip rate. The next example says the table below lists overhead widths in centimeters of seals measured from photographs and the weights in kilograms of the seals, and the study is listed there if you want to look into it. And so we have a table here that's going to be your overhead widths in centimeters and your weights in kilograms. And so we're going to have, this is going to be our X values and our Y values. Your book, and also with My Open Mom, is always pretty much going to have these listed in the same order as they would in an algebra class, which is always your X value first and then your Y value second. And so we need to take a second and enter in these numbers into L1 and L2. And from that, we can make a scatter plot. We're going to do the scatter plot by hand, and then we'll also do that using a calculator. Unfortunately, to turn things in, you are going to have to write them down. And so you would have to do a scatter plot on your own. So making our scatter plot, and from algebra, you are always going to have your X variable and your Y variable. So your X variable is on the horizontal and your Y variable is vertical. And so our X variable is overhead widths in centimeters, and then weight is going to be in kilograms. And so if we look at overhead widths, the smallest value that we have is 7.2, and the largest one that we have is 9.8. So I need to go from about 7 to 10. So I'm going to go ahead and start it at 7, and then we'll say 8, 9, and then 10. And again, if you want to, you can split this up any other way that you would like, counting by 0.2s or anything else. I'm counting by 1s, and I put little center dashes in there to count as 0.5s. Our weights for our seals, the smallest weight that we have is 116, and the largest is 245, so close to 250. So I'm going to count by 50s, and I'll make my smallest weight be 100. So 100, 150, 200, and then 250. And then every single seal is going to get 1 point. So 7.2 centimeters and a weight of 116. Do the best you can. It's difficult to exactly graph these completely accurately, but do the best you can. So the next seal is 7.4 and 1.54. And then the next one that we have is going to be 9.8 and 245. It's our largest seal. Then we have 9.4 and 202. We have 8.8 and 200. And then 8.4 and 191. So again, do the best that you can. And then the next part on here, part B, says to find the regression equation and then graph the regression equation on the scatter plot in part A. So your regression equation is going to be a line of best fit, and that line of best fit is going to go, it wouldn't be somewhere up above all those points or below those points, it's going to be somewhere in the middle. And so I don't know, I'm estimating it right now, but something along those lines. I'm going to use the calculator to find this more accurately, and I'll draw that in a little bit better. So from here, we need to put our data into L1 and L2. I will go through how to use the graphing calculator to create your scatter plot, and then we will also use that to find our regression equation, and then from there, we'll keep going with the problem. On our calculator, we're going to go to Stat, to Edit, and enter in our data into L1 and L2. L1 again is our X values, that's the overhead width, and L2 is our Y values, and that is the weight. To see the scatter plot, first of all, you need to be able to do it by hand, but to see the scatter plot on the graphing calculator, We're going to go to second, y equals, and select enter on plot 1. On plot 1, we're going to go ahead and make sure that it is turned on. We're going to go to type and make sure that first graph is highlighted. Our X list is going to be L1. Our Y list is going to be L2. And again, the markings is up to you and the color is up to you. From here, we're going to go to zoom. And we're going to go down to zoom stat. Select enter. And those 6 different seals, the plots for them should show up. If you wanted to, you could select trace, and that's going to trace and bounce from seal to seal to seal. And you can see the different X values and Y values down there for the overhead width and the weight. So in order to get our regression equation, we are going to go to stat, go to test, and go down to linreg t-test. On linreg t-test, we have L1 and L2 frequency set equal to 1 and rows not equal to. We're going to go ahead and tell the calculator to graph our regression equation. And I want it to graph it on our scatter plot that we just looked at. So for this one, we are going to go to vars. Make sure your cursor is in the regression equation spot. And we need to go to vars. Go over to yvars, select enter, and I'm going to tell it to graph this and put that equation in for y1. So select enter on y1. It should put a y1 here, and you only have to do this once on your calculator. If it is an app, it might be working differently, but if you have your own graphing calculator or if you're using one of the ones through Texas Instruments online, then it should be the same way. Select enter on calculate. And again, we get a bunch of different information here. We have, in order for our regression equation, we have our A value and our B value. And we also have our correlation coefficient, R. So from our calculator, we saw that the regression equation went somewhere through all those points. Again, do the best that you can by hand to graph that regression equation. And then remember that that regression equation is called y hat. So I'll go ahead and label that on my scatter plot. To see the regression equation on our scatter plot, after you run your linreg t-test, you need to go to zoom and go down to zoom stat. Select enter, and you should have those 6 points still on there, and then that regression line should be graphed. Part B says to find the regression equation and graph the regression equation on the scatter plot in part A. Well, we did that part already. So the regression equation, to find that exact equation of the line, from our calculator we get y hat is equal to, and we're going to round 3 decimal places. I have negative 156.879, that was the value of A, plus B, which is going to be 40.182, and then X, that's our value for B. Part C says, what does the slope and the y-intercept of the regression line represent in the context of this problem? So from algebra, we know that we had y equals mx plus b. And I'll go ahead and write that over here on the side. I'll change the color. So we have y equals mx plus b was from algebra. I want you guys to notice that m is what's in front of your x, and that's your slope. So for this, it's asking for what does the slope and the y-intercept mean. And so your y-intercept is the one that does not have the x value with it. And so for this problem, it's negative 156.879. And so it says, what does the slope and the y-intercept mean for this problem? So the easiest one to talk about is the y-intercept. So our y-intercept, and from algebra, we know that a y-intercept is when x is equal to 0. So in this problem, if you look back up at your table, your x value is your overhead width. So this is going to be when x equals 0. or for this problem, when the overhead width is 0, and then that y value that we have is going to be what we have for our weight. So if the overhead width is 0, the weight of the seal, so the weight of the seal is, and our y value that we have is negative 156.879. And does this even make sense? No, this does not make sense. So does not make sense. So this is saying that if the overhead width of the seal is 0, well then there is no seal, and the weight of that seal is negative, and we don't have a weight of negative. So a lot of times we have a y-intercept that does not make sense. We also need to discuss the slope for this problem. So for this problem, the slope is the value that is stuck with the x, so the slope. And for us, slope is going to be the same thing as, if you remember from algebra, rise over run, which was a change, and that's what delta is, a change in y over a change in x. And so our y variable for this problem is weight. So I'm going to say change in weight over a change in, and our x variable is overhead width. And so putting those numbers in, our change in weight over our change in overhead width is equal to our slope, and the slope value that we have is 40.182. And if you notice, I have slope is written as a fraction, and I have a decimal here. Don't worry, we won't convert. We're just going to go ahead and put a 1 underneath this. And so what this means is that if the overhead width was to increase by 1, and our units are centimeters, then the weight of that seal is going to increase by 40.182 kilograms. So we need to put that in writing. So if the overhead width, and it increases, and the reason why is because it's positive, by 1 centimeter, then the weight of the seal increases, and again it's increases because it's positive, by 40.182 kilograms. Part D says, what is the predicted weight of a seal that has an overhead width of 9 centimeters? So first thing is, anytime it says predicted weight, it's asking for us to find, and that's our y variable, y hat. And so anything predicted is a guess that we have, and we're going to have to be using our regression equation to figure that out. Since our overhead width is 9 centimeters, that's our x value, if you look back up above. So I'm going to take my regression equation, and I'm going to substitute in 9 for my x value. And working this out on our calculator, we get 204.759. Make sure you put the correct units with this. This is in kilograms. And this is how much that seal would weigh if it had an overhead width of 9 centimeters. And again, this is an approximation that we have. The next thing that we have is called a residual. This is the error value between the predicted value and the observed value. The residual is the observed y value minus the predicted y value. The criteria to determine the line that best describes the relationship between two variables is based upon residuals. The most popular technique for making the residuals as small as possible is the method of least squares, and that is why they sometimes call the line the least squares regression line. So if you notice, the residuals is the difference between those points that we have, which is our observed data, and the line, which is our predicted or approximated results that we have, like we just did in the SEAL problem. And so it says the smaller the residuals, the better that our line is going to be, and you can see that over here. It's a lot closer to that line versus if we have larger residuals. Analyzing residuals. 1, it says determine whether a linear model is approximate to describe the relationship between the variables. A residual plot is a scatter plot with residuals on the vertical axes and the explanatory variable on the horizontal. If the residual plot shows a pattern, so if we have some kind of pattern, such as a curve, then we're going to have a linear model is not appropriate. However, if the residual plot shows no pattern, then we're going to say a linear model is going to be appropriate. 2, to determine if the variance of the residual is consistent, we have a constant error variance or homoscedasticity on the residual plot if the spread of the residuals is increasing or decreasing as the explanatory variable increases. And then step 3 is checking for outliers. You will not have to create these on your own. This would be given to you in a graph, and you would have to analyze it on your own. And so if you notice that the first one that we have, there is no pattern. The second one is increasing without a bound. And then the last one has some kind of pattern there, and that's looks more like a parabola or something along those lines. So next thing that we have is 10.3, prediction intervals and variance. In the previous section, we saw a method of using a regression equation to find the predicted value of y, but it would be great to have a way of determining the accuracy of such predictions. So we have a prediction interval. This is a range of values used to estimate the variable, such as the predicted value of y in a regression equation. We also have a confidence interval. This is the range of values used to estimate a population parameter, such as p, mu, or sigma. Given a fixed and known value x naught, the prediction interval for an individual y value is, and this is going to look similar to what we did before with our confidence intervals. So we're going to have our y value is going to be between two things, and our y value is going to be between y hat plus our margin of error and y hat minus our margin of error. Next thing that we have is deviations, is a measure of difference between the observed values of the variable and some other value, often the variable's mean. So we have total deviations, explained deviations, and unexplained deviations. So total deviations, the deviations between the observed and the mean values of the response variable, is going to be total deviations is y minus y bar. Y bar is going to be that mean that we have. Explained deviations is the deviations between the predicted and the mean values of the response variable. And our predicted is y hat. Y bar, again, is our mean. And then unexplained deviations is the deviations between the observed and the predicted values of the response variable, which is y minus y hat, which again, y is our values and y hats are predicted. So the total deviations is equal to the explained deviations plus the unexplained deviations. You can see that in the equation below. It's also in the graph right below that, with the unexplained deviations, our explained deviations, and the total deviations all in here. I want you to notice that there is our mean, which would be y bar. We have our actual y value, which is our point here, which would be y that we would have. Either way you want to look at that. And then we have our estimated, which is that line that we would have, which is giving us the value that we have is y hat from that line. So right below this, it says total variations, explained variations, and unexplained variations. And so for all of these, it's the sum of the squares of the total deviations or the explained deviations or the unexplained deviation values. Next we have is the coefficient of determination, which we call r squared, and we saw this earlier. R squared is the proportion of variation in y that is explained by the regression line. It's exactly what we had back in section 10.1. And another way to get this is to take the explained variations divided by the total variations. And it says we can compute r squared by using the definition above, or we can square the linear correlation coefficient r. And that's what we did back in section 10.1. And so if r squared is equal to 0, the least squares regression line has no explanatory value. If r squared is equal to 1, the least squares regression line explains 100% of the variation of the response variable. And the closer that r squared is to 1, the better the line describes how changes in the explanatory variable affect the value of the response variable, the better the fit is. So you can go back and look at the problem that we did in this section in response to the bill and the tip amount for r squared. So there's pictures here with different values of r squared. You can notice if r squared is closer to 1, those values will definitely look a lot better, more like a straight line. And then we have r squared is closer to 0, that we don't have it explained as much. So we have another example that I'll go ahead and circle, and we'll work on this one together in class.